So picking up where we left off, question number 35. Most people got this one right. A program that was intended to cure a person's fear of spiders was offered at a local zoo. Volunteers with a fear of spiders participated in the program, which included holding a spider for 15 minutes. 1 month after they completed the program, the participants were contacted and surveyed about the program. Over 90% of the participants claimed they were cured of their fear of spiders. Based on the description of the program, which of the following statements is true? And we have people that were volunteers for the program. Where is that? Volunteers. The correct answer then is because the participants were self-selected, a person's desire to be cured could be a confounding variable. Number 36. More than half of us got number 36 incorrect. A police officer uses a motion detector to indicate whether a car is traveling faster than the speed limit. A speeding ticket will be issued to the driver of the car if the officer believes the driver is speeding as indicated by the detector. The situation is similar to using a null and an alternative hypothesis to decide whether to issue a ticket. The hypotheses can be stated as follows. Null is the driver is not speeding, and alternative is the driver is speeding. Which of the following best describes the power of the test? The power of the test would be to correctly reject the null hypothesis. That is what power is. So if you are correctly rejecting the null, that would mean that the null is false. If the null is false, then that means that the driver is speeding. Thank you. So this would be the probability of issuing a ticket to a driver who is speeding. Reaching the correct conclusion, where that correct conclusion is the alternative hypothesis. Right. Getting close now. Number 37. Number 37, most people got this one right. An agricultural scientist wanted to compare the effect of a new fertilizer to that of 3 older fertilizers, X, Y, and Z, on the growth of vegetables typically grown in small gardens. 200 green bean seedlings were individually planted in identical pots and randomly assigned to one of 4 groups of 50 each. Seedlings in one group were given the new fertilizer, and the 3 remaining groups of seedlings were given fertilizers X, Y, or Z, respectively. At the end of 4 weeks, all seedlings were dried and weighed. The scientists found that the mean weight of the seedlings in the group given the new fertilizer was significantly greater than the mean weight of the seedlings in the other 3 groups. The scientists concluded that the new fertilizer was more effective than the other fertilizers for all vegetables. Why is the scientist's conclusion not appropriate? Right here, he concluded that this was true for all vegetables, but he only did the test on what? He only did it on green beans. And so the experiment only included green beans, so the results cannot be generalized to all vegetables. They could generalize to all green beans, but you can't generalize to all vegetables. Number 38, most of us got 38 incorrect. In a physics experiment, 2 different methods were used to measure the angle of deflection when a subatomic particle collides with a certain material. 10 specimens of the material were used to compare the 2 methods. For each specimen, the angle of deflection was measured using both methods, right there. Definitely paying attention to that. And they said that this was for each specimen. What kind of a design are they talking about here? Paired. This is paired, matched pairs. For each specimen, the method used first was determined by the flip of a fair coin. The difference between the measured angle was calculated for each specimen. A test of the hypothesis that the population mean difference is 0 had a p-value of 0.082. The hypothesis test described had 3 components: the number of specimens, the sample standard deviation of the differences, and the magnitude of the sample mean difference. Compared to the test described, which of the following would have resulted in a smaller p-value? All right, so looking at this, the magnitude, hold on, where did it go? The magnitude of the sample mean difference, that would be my x-bar diff. Number of specimens would be n. And the sample standard deviation, that would be S of x bar. For all of these, except for the last one, what do we know about the number of specimens for all of these choices except the last one? Read through those choices. What is consistent for choices A, B, C, and D? Number of specimens. A says the number of specimens, skip a little bit, remained the same. Part B says the number of specimens, skip a little bit, remained the same. Part C, number of specimens remain the same. Part D, number of specimens remain the same. Part E is the only one where they say anything about the number of specimens being different, and they specifically say that it was smaller. If n gets smaller, what happens to your p-value? P gets bigger. If n gets smaller, p gets bigger. If n gets bigger, p gets smaller. So this is not going to be E. All right, number of specimens and the sample standard deviation of the differences remain the same, but the magnitude of the sample mean difference was smaller. So let's look at this. We're talking about calculating a t-score and then a p-value from a t-score. The bigger t is, the smaller p is. So t goes up, p-value goes down. X bar of the differences minus mu of the differences over S diff divided by square root of n, not just n, sorry, square root of n. So that's how we calculate a t-score. So we want the biggest t-score we can possibly get to give us the smallest p-value that we can get here. So changes in which of these will result in a higher t-value. And we said that we were doing this. Population mean difference was 0. That's what our null hypothesis is. So that would make this x bar diff over S diff divided by square root of n, because the mean of the differences would be 0. So that'd be the same as just kind of getting rid of that. So x bar diff, if my numerator gets bigger and everything in the denominator stays the same, then my t-value is going to be bigger, right? If the standard deviation, the sample standard deviation gets bigger, this right here, that makes my denominator bigger. What happens to my overall value if the numerator stays the same but the denominator gets bigger? Yeah, my number overall gets smaller. So I want something that's going to maximize my x bar and minimize my S. So here we have number of specimens and sample standard deviation of differences remaining the same. but the magnitude of the sample mean differences was smaller. If my numerator gets smaller, my overall value gets smaller. So this would not be A. The number of specimens and the magnitude of the sample mean difference remain the same, but the sample standard deviation of the differences was larger. If the denominator gets larger, then the test statistic gets smaller. C, the number of specimens remained the same, but the magnitude of the sample mean difference was smaller, and the sample standard deviation of the difference was larger. Well, that's two changes right there that would both make my t-value smaller. So it is not that. And then D, the number of specimens remained the same, but the magnitude of the sample mean difference was larger. This is my numerator. And the standard deviation of the difference was smaller. There's my denominator. That is the correct choice. It has my numerator getting bigger and my denominator getting smaller, both of which would result in a higher test statistic, a bigger t-value, therefore a smaller p-value. 39, next to last question. More than half of us got this one incorrect. A polling agency reported that 66% of adults living in the United States were satisfied with their health care plans. The estimate was taken from a random sample of 1,542 adults living in the United States. And a 95% confidence interval for the population proportion was calculated as 0.636 to 0.684. Which of the following statements is a correct interpretation of the 95% confidence level? So we only want the interpretation of what it means to be 95% confident. When we talk about a confidence level, we're saying if we were to repeat what we did here over and over and over again with samples selected in a similar way, about 95% of them would capture the true population proportion. That does not mean that there's a 95% chance that my interval captured the population proportion. But if we were to do this 100 times over, about 95 of them would capture whatever the true population proportion is. And so that is choice B, right here. Approximately 95% of random samples of the same size from the population will result in a confidence interval that includes the proportion of all adults living in the United States who are satisfied with their health care plans. This is the parameter. When we're talking about confidence levels, we are never talking about probabilities. This is not the chance that the population proportion is in our interval, so that is why A is wrong. Approximately 95% of samples of the same size from the population will result in confidence interval that includes the proportion of all adults in the sample. Every confidence interval will contain the sample average, or the sample proportion rather, because that is the point estimate. That sample proportion will be in the center of whatever interval is calculated. So for every confidence interval ever, the sample proportion is smack dab in the center. That is not what it means to be 95% confident. D says approximately 95% of all random samples of adults living in the United States will indicate that between 63.6% and 68.4% of the adults are satisfied with their health care plans. We are not guaranteed to have the same endpoints every time we do this 95% confidence interval. In fact, I would expect that for 100 different samples, I would have 100 different similar but different endpoints for my confidence interval. They're going to be close, they're going to be around each other, because again, 95% of them will capture the true population proportion, but these intervals will not all be the same. Approximately 95% of all random samples of adults living in the United States will result in a sample proportion of 0.66. Where did they get that 0.66 from? Anybody know? This is the sample proportion. That's the p hat. If you look up the interval that was calculated, 0.66, or they even say up here at the very top, 66% of adults. We don't know that our sample proportion will be in 95% of these intervals, but whatever the true proportion is, will be. Does that make sense? Okay. And last one, number 40. We're about half and half on number 40. A survey was conducted in a large city to investigate public opinion on banning the use of trans fats in restaurant cooking. A random sample of 230 city residents with school-age children was selected, and another random sample of 341 city residents without school-age children was also selected. Of those with school-age children, 94% opposed the banning of trans fats, and of those without school-age children, 147 opposed the banning of trans fats. An appropriate hypothesis test was conducted to investigate whether there was a difference between the two groups of residents in their opposition to the banning of trans fats. Is there convincing statistical evidence of a difference between the two population proportions at a significance level of 0.05? Okay, so we have a difference of proportions. So we have a p hat 1. That'd be, let's see, random sample with school-age children, random sample without school-age children. Okay, so 230 residents with school-age children. Of those with school-age children, 94 opposed. So 94 out of 230 is my first p hat, which gives me about 0.409. And then p hat 2 would be the ones without school-age children. Said random sample of 340 city residents without school-age children, and 147 opposed the banning of trans fats for the people that did not have school-age children. So 147 out of 341, which is a p hat 2 of about 0.431. All right. So then I need p hat 1 minus p hat 2. That'd be 0.409 minus 0.431. That gives me negative 0.022. We're going to need the standard deviation for p hat 1 minus p hat 2. That would be the square root of, we're going to use p hat combined here because we're doing a significance test. So to get p hat combined, do 94 plus 147 over 230 plus 341. I end up with 241 over 571, or a p hat combined of 0.422. So that's what we're going to use for our standard deviation of p hat 1 minus p hat 2. I've got 0.422 times 1 minus 0.422 over N1, which was 230. Plus, and then we do the same thing for our second population, p hat combined times 1 minus p hat combined over N2, which was 341. We end up getting a sample standard deviation of about 0.0421, and so then I can do normal CDF. Lower bound would be something enormous. It's like negative 999. There's my lower boundary. Upper boundary of negative 0.022. And then mean and standard deviation, 0.422 and 0.042. I don't have enough room to write this all on here. And we end up getting a p-value. We're doing two-tailed, so we have to multiply it by 2. We get a p-value of about 0.601. And so are we going to, do we have convincing statistical evidence? We do not, because we're testing this at the 0.05 level. The probability of observing a difference at least as large as the sample difference if the two population proportions are the same is greater than 0.05. And that finishes all the multiple choice. All right, so I need you guys to come up. I think we have just enough. Let me double check this count, but I'm pretty sure that we have the same number of tests here. 8, 10, 12, 14, 16, 17. We have 17 people in the room today. I have 17 tests that need to be graded. Please come up and grab a test. Just make sure that it is not yours. And a red pen. Grab a test and a red pen. Just make sure it's not your test. Does everybody have a test to grade? Everyone's got a red pen. Fantastic. So we're going to start grading these free response questions. Please go ahead and open it up so that you are looking at this person's answer for question number 1. But then I'm going to want your eyes up here. We're going to look at a model solution, and then we are going to look at the rubric and understand exactly how we need to grade this first question. So sample answer. Question number 1. This was one where you have to do the 4 C's: choose, check, calculate, and conclude. So choose 2 sample z-test for P1 minus P2, where P1 minus P2 is the true difference in proportion of all exercise center members who would be interested in taking online fitness classes, aged 18 to 55 minus age 56 and older. P1 minus P2 equals 0 is the null. P1 minus P2 does not equal 0 is the alternative, so we're going to have to calculate P hat combined. Whenever you have a P1 minus P2 equals 0 situation, that is when you have to do the P hat combined, and that is the only time when you have to do P hat combined. Check random independent samples. 170 is less than 10% of several thousand members ages 18 to 55. 230 is less than or equal to 10% of several thousand members ages 56 and older. And then we have to check our large counts, making sure that these are more than 10 for all 4. Success, fail, success, fail. Calculating, including a picture. We have our z-score of negative 0.92. and a p-value of 0.3576. Here, this is what they got from doing p hat 1 minus p hat 2. Where did they go? I didn't write it down. Anyway, that's what that is. And then conclude, because 0.3576 is greater than 0.05, we fail to reject the null and do not have convincing evidence of a difference in the proportion of all exercise center members ages 18 to 55 years who would be interested in taking online fitness classes, and the proportion of all exercise center members ages 56 and older who would be interested in taking online fitness classes. Right, so that is what the answer to this question should have looked like. I'm going to pass out the rubric, and we're going to look at the rubric together so that you can go in and score piece by piece this question. You will be giving this person a score at the end of 0, 1, 2, 3, or 4. Coming back are the rubrics. Please open up the front page so that you are looking just inside that front cover. And that will take us to the rubric for the first part of this question. All right, so scoring guidelines says that each section is scored with an E, P, or I. And then when we get to the end, we will look at what constitutes a 1, 2, 3, and 4. So things that you need to look for in your person's answer, there needs to be 3 components met. And if they meet these 3 components, they get an E. Identifies a 2-sample z-test for a difference of population proportions by name. So they call it a 2-proportion z-test or a 2-sample z-test, or by formula. So if they didn't have 2-sample z-test or 2-proportion z-test, but they did have the whole formula written out where they calculated that z-score, they would get credit for that section. Second component states a correct null hypothesis of equal proportions, or P1 minus P2 equals 0. That's the same thing as equal proportions. And a correct 2-sided alternative hypothesis of unequal proportions. So P1 minus P2 does not equal 0, or P1 does not equal P2. Provides sufficient context by referencing the 2 groups, 18 to 55 years of age and 56 years of age or older, and the populations, all exercise center members. So this would be in that definition of P1 minus P2. Go ahead and look through, see if they have all 3 components. If they do, then they get an E for that section. Go ahead and write a capital letter E there. If the response satisfies 2 of these 3 components, then they get a P. And if they only meet 1 component or no components, they get an I. And if you have a question about how to score yours, I will move around the room and offer assistance.
So they did all this right, but they just didn't put Z. So would that still get them?
They have the whole formula here? If they've got the whole formula here, yeah.
That right
Test
there
statistic. Yes, I would count that.
Okay,
I
wasn't
count that.
sure. I was like,
yep.
It doesn't say it, but
it should say Z there, but because they have the formula, they saved themselves on that.
Okay.
Yep. That would be an incorrect there.
So there would be.
So overall, if they met the other requirements, then they'd get a P on that section. All right. Yep. Yes, if they have the formula with all of the numbers plugged into it, but it is the correct formula, then they would get credit for that. Yes, that should say not equal. So we do not have unequal, we do not have the name test. What is unfortunately You did a lot of good work. For that section. All right. Moving on to the next section of this same question. Still looking at the same question. Hopefully not. Section 2, the independent, let's see, essentially correct. We needed 4 components here. They needed to have checked the independence condition by referring to the 2 samples and indicate that there are more than 1,700 exercise members from 18 to 55 and more than 2,300 exercise members ages 56 years and older. So they need to show their 10% condition. They do not have to say 1,700 and 2,300, but they do need to have like 170 is less than or equal to 0.10 of all whatever. And they need to check the independence on those 2 random samples. So to give you an idea of what that piece needs to look like, they need to show somewhere that they checked independent random samples, and they need to show their 10% condition. That's component 1 here. Component 2 checks that the sample sizes are large enough, so checking large counts here. Component 3 correctly reports the value of the Z statistic and correctly reports the p-value. So you need to check large counts. So random and 10%, they have combined into 1 component. Large counts they have as a component. The Z-score by itself, Z equals, is one of the components. If they do not have a Z equals, they do not get that component. And then the p-value of 0.3576. The Z statistic and the p-value need to be labeled. They can't just be random numbers there. And then they need to have this piece here. If they have all 4 of those components, I went to the wrong section, thank you much. If they have all 4 of the components, then they get an E for that section. If they have 2 or 3 of those components, they get a P. And if they have 1 or none of those components, then they get an I. If you need help scoring yours, I'm absolutely willing to help. We are supposed to use p-hat combined.
Okay, so that one. And yes, if they have test statistic equals blah blah blah, then it equals, but it's not the same value. But this is like almost close to it. Does that also count?
Yeah.
Let's look in the notes here, because usually they'll give a range. Samples of quantities, 50%.
They didn't get it.
Rounded from 0.92. P-value of 0.3576. Which would be okay if they have the positive. It depends on the direction they're subtracting. Yeah, they did 0.34 minus 0.3. They did 56 minus 18, so they flipped around. So I would expect that to be a positive value. Yes. Yes. All right, does anybody else need help scoring theirs? I'll be right there.
Oh my God, I work
You have to use the p-hat combined. If they did not use p-hat combined, then they would not get that correct. So it should be p-hat combined 0.325. The same thing for the where did they calculate p-hat? Okay. It looks like instead of adding and numerator, numerators and adding the denominators and coming up with that. They did this fraction plus this fraction. So that would be incorrect. But they tried to use p hat combined. So I would still give them credit for this section. Because the only thing that I'm seeing that absolutely was definitely a markdown, they used wrong values, was if they used p hat 1 and p hat 2. Have to use p hat combined for your large counts. Yes. Oh, yeah. Yes, it is going to affect the attendance.
I think so, yeah. I couldn't figure it out, so I just gave up.
Yeah, so they would get turn off to the Z-score, so that is incorrect. But if this is consistent with this, which from the work they're showing, that looks consistent, they would still get credit for this work. So that, because they got the Z statistic wrong, they would get a P. Yep. All right. Does anybody else have questions over how to score section 2? All right. Yes. Oh, I'm sorry, Tom. Oh, it's sorry, it is right. I'm looking at the wrong spot. If they only missed that one piece, then they would get a P on that. Yeah. So one of the big takeaways that I want you guys to have from scoring this question in particular is how important it is to not just write numbers down on the page, but to have them labeled. Make sure that your Z test statistic you have labeled as a Z equals. Remember, you can make the calculator spit this number out at you. You don't have to calculate this by hand. Remember, you can do a Z test underneath the test section. So stat and go over to test. You can enter those summary statistics, and you can make it calculate both the T and the P value. Or sorry, this would be a Z and a P value. But make sure that these numbers are labeled. It is absolutely essential that these numbers are labeled. All right, section 3. This is the conclusion. There are 2 components that you need to have here. Provides a correct comparison of the p-value to the alpha value, saying that the p-value is greater than alpha. And a correct decision about the null and or alternative hypothesis, and states a conclusion in context consistent with and in terms of the alternative hypothesis using non-definitive language. So you have to have a because p is greater than alpha, or if they found a p-value that was smaller, they need to stay consistent with whatever they said earlier. So either p is greater than alpha or p is less than alpha. And then they have correctly made the decision to reject or fail to reject. So if they found a wrong p-value and they said that p was less than alpha, but then they correctly said that because p is less than alpha, we would choose to reject, then you can still count that in this section as correct. They made a mistake earlier, but that does not necessarily mean that they have to miss everything here. They should have found that p was greater than alpha, and so we are failing to reject. And then it says the other component of this that they needed to have was stating this conclusion in context, consistent with and in terms of the alternative hypothesis. So we do have convincing evidence that, and then have their context that is related to their alternative hypothesis, or we do not have convincing evidence. In this case, we would not have convincing evidence. Yes?
Do they need to add that to get credit or no, because it's not in the rubric?
It's not in the rubric, so for this one right here, because that idea was scored up in that first section, if they don't have that here, they can still get full credit on this part. Yes. They needed to have both components to get an E. If they got just one of these 2 components, then they get a P. And if they don't have either component, then they get an I. All right. Does anybody need any help with how to score section 3? All right. Yes.
So for section 2, if we would have had to make a confidence interval for that, would we have used p-hat combined to check the large counts?
No. You would use P1 and P2, P-hat 1 and P-hat 2 if it was an interval question. Yes. The only reason that we use P-hat combined on the tests is that null hypothesis is that P1 and P2 are the same. So we're basically trying to equalize any differences that there are between these two. One of the things I do want to warn you guys about is when you calculate P-hat combined, make sure that you are adding the way little kids want to add fractions, but not the way you actually add fractions. This is the only time where the second grade method of adding fractions is the right way to do it. You add your numerators, that becomes your new numerator, and you add your denominators, that becomes your new denominator. You're not taking fraction plus fraction. You're doing top plus top over bottom plus bottom. And I know that gets a little confusing because everywhere else in math we tell you absolutely please don't do it that way. All right, so please now give them a score of a 1, 2, 3, or 4. If they got all 3 sections as an E, they get a 4. If they had 2 sections as E's and only 1 P, then they get a 3. There's a couple ways to get a 2. You have 2 E's and an I. You have 1 E and 2 P's, or 3 P's. All of those are ways to get a 2. And then a score of 1 would be 1 E and 2 I's, or no E's and 2 P's.
That's what mom was talking.
All right. So 3 E's, 2 E's and a P, 2 E's and an I, 1 E and 2 P's, or 3 P's. Down here for a 1, you get 1 E and 2 I's, or 2 P's and 1 I. Is everybody good on that piece? All right. Yes. Oh, I can take that. Thank you. All right. Let's start looking at the next question. I don't know if we'll get all the way through it, although fingers crossed, I'd really like to. Question number 2. This one was the Bottles fundraiser, and I apologize, you guys had to draw those bar graphs in by hand. So the bar graph should look something like this for part A. For part B, should have no, the elementary school administrator is incorrect. While the elementary school sold a higher percent of small bottles, the middle school sold more small bottles. Suppose X equals the total number of bottles sold at the elementary school, then the number of small bottles sold is 0.50X. The middle school sold 3 times as many bottles, so they sold 3X, with 1/3 times 3X being X, where that is the number of small bottles that the middle school sold. Since X is greater than 0.5X, the middle school sold more small bottles. Part CI, high school A sold a greater proportion of large bottles because 0.7 is greater than 0.6. Part II, high school B sold a greater number of large bottles because the area of the rectangle for large bottles sold at high school B is greater than the area for large bottles sold for high school A. All right. So looking at these sections, for the bar graphs, 2 components here. The elementary school's segmented bar graph is correctly partitioned according to the given proportions. So the elementary school, they should have a section for small bottles that goes up to 0.5. They should have a section for medium bottles that takes up a total of 0.3. And they should have a section for large bottles that takes up an area of 0.2. And they do need to indicate like which is which. So there needs to be some kind of key on there, not just the partitions, but some type of key. And then for the middle school, 1/3 and 1/3, or 1/3 and 2/3. Middle school segmented bar graph is correctly partitioned to create 3 equal areas. So they have to have a correct elementary school segmented bar graph and a correct middle school segmented bar graph. If they got both of those components, give them an E. If they got only one of those two components, give them a P. And if they didn't get either one, give them an I. You guys ready for the second part? All right. Section 2. We needed to have 3 components. They needed to state that the elementary school administrator is incorrect, so somewhere in there he's wrong. Provides correct mathematical support, verifying the middle school sold more small bottles than the elementary school, consistent with the response to component 1. And you have to include context. So they could do this the way I showed on the model solution, where they had 0.5 times however many bottles, and then 3 times as many bottles would be 3x times that 1/3, and then they could show that inequality. Or they could put in a sample number. They're like, pretend the elementary school sold 100 bottles, or sold 100 bottles total. Then 50 of them would be these small bottles, and for the middle school, they sold 300, so 100 of them would be the small bottles. So some kind of mathematical justification for why this administrator is incorrect. All 3 components, they get an E. If they only satisfy 2 or 3 of these, then they get a P. And 1 or none gets an I. Does anybody need help scoring this section? All right, we are going to get through this question. Let's look at section 3. This was part C. There were 4 components that were being looked for here. There they are. Oh, come on. In part CI, the response indicates that the high school A sold a greater proportion of large bottles. In part CI, the response bases the reasoning on the height of the rectangles or the relative frequencies representing large bottles. So they need to state clearly that it was high school A, and they need to base their response either on the height of the rectangles or by comparing the relative frequencies. And then in part CII, the response indicates high school B sold a greater number of large bottles, and the response indicates the rectangle representing large bottles for high school B is larger than the rectangle representing large bottles for high school A. If they have all 4 components, then they get an E. If they have 2 or 3 of those components, then they get a P. And if they have 2 or 3 of those components gets a P, and if they have 0 or 1 of those components, then it gets an I. Does anybody need help scoring this last section? High school B sold a greater proportion because the variance on the mosaic plot. 70% of their large bottles. They got the I and II sections switched. Unfortunately, that would be an I.
How's it wrong? That's the same.
Yes.
Okay, so everything else is right, but it doesn't have the key, so I don't know if it's like.
I'd give them a P on that section then.
Okay. And then maybe it's because I don't know the square thing back, but there are numbers here, but I don't know if it's like.
For that part?
Yeah.
Let me see if I can pull that up. That's 2023. All right. Real quick, while I'm looking for this, you can go ahead and give your person a score. Three parts essentially correct, they get a 4. 2 parts essentially correct, 1 part partially correct, they get a 3. Two E's and no P's, or 1 E and 2 P's, or 3 P's, all score a 2. 1 E and 2 I's or 2 P's and 1 I gets a 1. If you have a score on yours, you can come and put your pen and your test booklet up here. That'd be a 0. Yeah, that'd be a 0. Yes, sorry, make 2 piles for me, one that's the rubric and one that's the test booklet. Put the rubric on desk 3, please. 1 or 2 parts partially correct, so that would be a 2. Yep, 1 part essentially correct and 1 or 2 parts partially correct.
Okay.
Yep, good question.
I was like, there's one of each, so.
Okay. Jalicia, the only place that I can find numbers, at least on part B, is just up in the question stem where they're talking about how you would do these bar charts. Yes. No. So in general, because you've got that, like 50% of what they sold was the small bottles and 33%-ish was the small bottles for the middle school, but the middle school sold more. So coming up with some numbers to use there or using X as a general variable.